Good afternoon, guys. Gonna go ahead and get started. Opening up kind of class, what we're gonna be talking about today and then honestly all next week is applications of the first fundamental theorem of calculus, which we know what the first fundamental theorem of calculus is. It tells us how we can evaluate the definite integral. This is probably one of the more important units. Obviously applications, like that's the whole point of learning calculus. But these are also like no single application will be done exactly the same. We're not going to get into the actual word problems today. I am going to save that for after the long weekend. Instead for today, I just want to focus on like understanding a little bit more in depth the first fundamental theorem of calculus, and then also start talking a little bit about units. And then we'll also look a little bit with the graphing calculator as well, since this will be really the first topic we have that really is going to be graphing calculator heavy. So why is this important? Like clearly it's applications, but also on the AP exam, the first or second free response question will always be something with this topic. It's either something that students either know or they don't know. And they usually come up with some like crazy questions. Like obviously last year was a little bit of a weird year, but I think 2 years ago the question dealt with like fish swimming into a lake and out of a lake. So like they come up with some crazy stuff. But at the end of the day, we're using integrals and derivatives to kind of solve the question. Before we get into the notes, also just wanted to like briefly mention the quiz. Not quite done grading the quiz. I think I have just a few more students left in this class to finish grading. Once I get everyone's graded, I will post the answer key so that you have it. And then also, I will probably say many of you probably did not do as well in the quiz as you normally do, which honestly happens frequently on the first quiz of the second semester, especially with that second FTC and kind of dealing with the applications of it. Just so you're aware, I am doing the same thing I did first semester, where I will let your test grade replace your quiz grade if you do all of your homework, all the way up to a 100, of course. But today we are going to go ahead and start looking at these applications of the derivative. And I say application of the derivative because really we are going to be doing a lot with derivatives and integrals. And so the first thing I want to do is just kind of review the first fundamental theorem of calculus and kind of look at it a different way. Did notice in third period when I did this, some of these notes, for whatever reason, the first few of them got out of order when I copied it over. So you can kind of see the order that I'm going to be doing in. We're going to do the first FTC 3 versions, example A, example B, and then talk about units. I think example B somehow got stuck in this one, and then those were just all out of order. So what is the first FTC? We did this first semester. In fact, I just covered it in my AB class. But we know that the first fundamental theorem of calculus tells us how we evaluate a definite integral. When we're evaluating a definite integral, we know the first thing we want to do is, of course, find the antiderivative. And then when we evaluate it, we plug in the top number minus plugging in the bottom number. I'm going to write that again, but using the derivative because that's going to connect more closely to what we're going to be talking about. So when I integrate f prime, I know that's going to give me just f of x, and we need to plug in the top and the bottom. So plugging in the correct order, we have f of b minus f of a. Focusing on this integral portion, so we can kind of see that when we integrate over a region f prime, that does give us the original function, that does give us f of x. And then when we plug it in, it's going to become f of b minus f of a. And we can look at that as kind of like an equation. The integral from a to b of f prime is equal to f of b minus f of a. So treating what I highlighted as kind of like an equation, if you were to solve for f of b, you basically just add this f of a to both sides. Adding f of a to both sides, so you would end up having that f of a added to the integral from a to b of f prime of x dx. That version of the first fundamental theorem of calculus is going to be super powerful to us, especially when we're looking at these formulas and the word problems. So it's still the first FTC. I'm going to kind of call it the first FTC rewritten. Some things I do want to kind of point out and make sure you notice about it. So this is f of b, and that's going to match the top number on the integral sign. Then we also have this f of a, which is matching the bottom number on the integral sign. We're going to think of this f of a as kind of like the start, probably better called the initial condition. And so you can kind of see we have like this initial condition plus the integral of the derivative will give us the y value, what f of b is, of wherever that integral is stopping at. And that's going to be really, really powerful for us to solve a lot of different types of problems. Before we get to the word problems, I just want to do an algebraic example first, and then we'll kind of see why that rewritten version of the first FTC is so useful. Which brings us back to some stuff we did in Unit 5. Here's a no calculator example of where that formula might be useful to you. To be completely honest, it's definitely a lot more useful when you can use a graphing calculator. But for the sake of kind of seeing why it works, I have this f prime of x, chose a pretty easy one to deal with. F prime of x is equal to this 4x plus 3. I give us an initial condition of f of 2 is equal to 1. And then what am I trying to find? I'm trying to find f of 3. So the old way we would have had to do this problem is we would know that, of course, f of x would be equal to this integral of f prime. And we would have to first integrate f of x to give us, or excuse me, to integrate f prime to give us f of x. So that would be 2x squared plus the 3x plus c. That is the general solution for f of x. Using your initial condition, 1 is equal to 2, plugging in 2 for x. And then we can easily solve for c. That's going to be 1 is equal to 2 times 4, 3 times 2, plus c. And then solve for, we do see that c is equal to negative 13. And then we can go ahead and use that new function we have to find that f of 3. So what was f of x finally? F of x was equal to 2x squared plus 3x minus 13. And then I can use that to find what I'm looking for. Which that's going to be 2 times 9 plus 9 minus 13, which is 14. And that is the old way we did those problems. The new way is using this rewritten version of the fundamental theorem of calculus. So I'm going to show you how it works. Again, it's definitely a lot messier when you're doing it, I think, by hand. The calculators when it's a little bit more powerful, but I do want you to see that we will end up with the same answer. So again, just what that formula state again, if I want to find f of b is equal to f of a plus the integral from a to b of f prime of x dx. What is the f of b I'm trying to find? I'm trying to find f of 3. Well, if I start at f of 2, I'm going to integrate this from 2 to 3 of the derivative of f. And then just kind of plug and chug, work it out. We will see that f of 3 is 14, but we can kind of see this skips, in some ways, some steps, introduces other steps where we end up with the same answer. So we have this f of 2, which was 1, plus the antiderivative. Don't need a plus c for this one. And then we can go ahead and plug in the top minus the bottom. So I have that 1 plus 2 times 9 plus 9 minus 2 times 4 plus 6. Solving that out. Clearly I'm cheating because I know the answer, but that is going to be 14 as well. So now we have kind of two ways of using that first fundamental theorem of calculus. Like the first one, we never really had a definite integral. We used an indefinite integral, found the general solution, and then we used that solution to find the particular solution, which we then use to do the value. With this new version of the first FTC, we just used in some ways the definite integral, and then basically worked it out, and that's where the answer came from. So that's kind of the two formulas that we have, the two ways of doing this. Again, I would never tell you which way to do it if you're doing it by hand. Personally, I would probably do it the old way just because it's pretty straightforward, I think. But we do see that we get to the same answers. Questions so far? All right, so let's go ahead and look at why this might be useful. Again, this might be a little bit further down in your OneNote because of how it was shared. This is going to be one that is calculator active. And so we will go to the graphing calculators in a second, but I want to kind of show you why it would be useful. So looking at this one, we have f prime is equal to the sine of e to the x. I have that f of 4 is equal to 5, and I want to find f of 1. Now, if we were to do this the old way, well, we know that first we would need to find f of x, which would be the integral of sine e to the x dx. And then you would have to try to find a way to integrate the integral of sine e to the x. Now, I'm going to be honest, we could go ahead and try doing like some integration by parts where we have like a single term integral. I'm going to go ahead and tell you right now it's not going to work out too nicely for us. In fact, this is one that we really can't do by hand. So like when I find my u and my dv, we have the du and the v. So kind of writing this one out, I have u times the v minus the integral of v du. And this is where I'm going to stop. Because if you're looking at this one, this integral is now like integration, and there's like 3 parts there, and that's just like not something we can do by hand. In fact, this is one that we cannot integrate using regular methods by hand. So there's no way to find a general solution for f of x. There's no way to find a particular solution for f of x. So then there's definitely no way to find what f of 1 is. Where the rewritten version of the first FTC becomes powerful is we can use it, and using our calculator, help us jump directly from the derivative to some value in the original function. So again, showing you the setup, we have, and I'm just writing it down one more time till we know it for certain, f of b is equal to f of a plus the integral where you start at, what you're trying to find, of f prime of x dx. We're trying to find f of 1. We were given f of 4. So I'm going to integrate this from 4 to 1. I know that's backward, but that's the order that we're going to use. And I'm going to go ahead and fill in f prime of x here, which is sine of e of x dx. F of 4, I'm going to go ahead and also fill in, which is 5. Again, things that should always match when you're doing it. F of 4, the initial condition should always match the bottom number on your integral sign. And then what you're finding should always match the top number on that integral sign. And then literally how we're going to finish up this problem is we're going to just type this into our calculator, and that's going to give us an answer. It's not a very nice integral, but it is going to give us an approximate answer. Some things I do want to talk about with using the calculator first before we actually go to the calculator. In AP Calculus, we will always use radians. We will never be in degrees for this class. You will always round to 3 decimals. If you round to 2 decimals, your answer will be marked wrong on the AP exam. I will treat the same way. We want to be exact to 3 decimal places. And I do want to be clear with some things about the calculator. The calculator is not going to tell us what f of x is. We can only jump directly to like that numerical value of f prime. So your calculator cannot do indefinite integrals. Your calculator can only do definite integrals. How do we get to those definite integrals? I'm going to go through the steps virtually, and then I'll switch my screen and show you my calculator. But you're going to hit the math button. And of course, making sure that you're in radians and all that. And then you're going to scroll down, or probably easier just to hit option 9, which will look like function integration. And then two things you'll see. If you have an updated calculator, it looks pretty nice. You'll basically see like the integral sign, and you have just a bunch of stuff you'll have to fill in. If you have a non-updated calculator or a TI-83 that can't be updated, you'll just see this notation. You have to kind of fill in some things, which I know is kind of gross, but you'll still get the same answer. The order you fill it in will be very particular. So you're going to put the function in first. You get to tell the calculator what the variable is, and then you have your lower limit of integration, comma, your upper limit of integration. So if I'm putting this into my calculator, and again, the calculator is not on my Surface. I just have it on my Dell, so I'm going to switch computers real fast. So there's my calculator. It's probably really small on your Surface. I am in radian mode, but I am going to go ahead and use this to evaluate my integral. So the integral that I'm evaluating, I'm going to hit math 9. This is the integral from 4 to 1. Again, the order matters. Of sine, let me try that again. This is the integral from 4, there we go, to 1. The function that I'm integrating is sine e to the x. This is with respect to x, have to fill that in. And then I hit enter. And so this is basically going to be 5 plus that number. I could have also typed it in all at once and maybe saved a little bit of time. So that's what f of 1 is equal to, and then hit enter, and then the calculator will do it for me. The more complicated your integrand is, sometimes that takes a little bit longer to do. This one for the calculator was pretty simple. And again, we're going to round it to 3 places. So I'm going to round it to, I have 5.243. You can either round that last decimal place or just write down the first 3 decimals you see, which this one didn't round anyways because of that 1, but 5.243. So that's really what we're going to be using on the calculator. We'll get very familiar with that math option 9. Some other calculus things your calculator can do. Number 8, some people use. Again, most of the AP exams, no calculator, but numerical derivative. Your calculator can't find f prime of x, but it can find the derivative at a point, and you kind of do it the same way. Like if I want to find d dx of, I'm just going to do something easy, x squared, and I say, well, what's that derivative at 7? My calculator can do that. Of course, that's an easy one to do by hand, but that's just some other things that your calculator can do. So it can't do algebraic manipulation, but it can tell us the derivative and the integral at a point. So then going back to my notes, I have my final answer that I wrote down while I had the screen switched out. F of 1 is approximately 5.243. And where we're headed with this is eventually like f and f prime are going to represent some sort of function modeling some scenario. And we're going to have to do like integrals and derivatives to answer the question. Any questions on anything on that slide?
Will we get points taken off if we don't put the approximate sign?
You wouldn't.
Okay.
All right, so let's go ahead. So I'm not doing any word problems today. I just want us to get us ready to do word problems on Tuesday. So the next thing I want to do is just talk about units. So we haven't used units in a lot of problems that we've done in this class so far. A lot of questions for these problems are pretty much going to always require you to include your units. And my surface is frozen. There it goes. So when we're using units, so again, I took some questions. I literally just deleted all just the word problem stuff, and I just left over the variables and the units, just so we can talk about how we can actually use the calculus to determine the units that we need to use. For example, if I say that t is some variable and it's being measured in seconds, and v is measured in meters per second, chose a PVA one. I think most of us are kind of familiar with that. We can actually use the calculus notation to figure out what the units should be. So I know we all know that V prime is the same thing as acceleration. And I know that we all know what the units of acceleration are. But say we didn't, we can use the calculus to make sure we get the notation and the units correct. For example, if V is in meters per second, V prime, another way to write V prime is dV over dt. dV is like a change in V. So we know that dV is basically in meters per second, and that's over dt. dt would just be in seconds. So we basically have our answer. V prime would be measured in meters per second, which is more commonly written as meters per second squared. That also works when we're doing the integral. For example, we know that the integral of velocity is going to give us position. So we could probably easily figure out what those units would be. But I can also use just the format of the integral just to check to know what the units would be. And what I mean by that, v of t is measured in meters per second. Here's why that dt is important. dt is time, it's measured in seconds. Well, what's meters per second times seconds? The seconds would cancel out and we would be left with meters. That's expected because what would position be measured in? Meters. For one that's not as familiar, again, I deleted all the word problem, but I have t is measured in hours and p is measured in people. And I said, well, if we find the derivative of this function p, what would be the units of our answer? Well, p prime is the same thing as dp dt. dp, p is being measured in people. dt is being measured in hours. So what will be the unit of measurement for p prime? It will literally be some sort of rate, people per hour, which I think makes sense if we think about the derivative as a rate of change. Can do the same thing when we have the integral. If I integrate p with respect to dt, we already said that p of t is people, dt is hours. Kind of a weird unit of measurement, but basically the integral of this p of t function would basically be people hours, which is related to work for those of you in physics, but for us, we're just going to say, like, in general, that's what the units of measurement for that one would be. Questions on those four? All right, try those last four for me. I have two more functions described, and I want you to figure out what the units would be of the derivative of that function, and then what the units of measurement for the integral of that function would be. So if I have c double prime is the derivative of c prime, which was given to us. It tells us that c prime is measured in dollars per foot. So c prime, again, dollars per foot. dx would then be measured in just feet, based off of what was given to me. So C double prime will be dollars per foot, probably more commonly written as dollars per a feet squared. Weird unit of measurement, but that's going to be the unit of measurement for C double prime. For C prime, we already integral of C prime, we have dollars per foot, dx is feet. So what would be the integral of C prime? It would be something just measured in dollars. This does bring us to something that we'll see a lot of in this topic, is that when we integrate a rate, so in this case, C prime is representing a rate because it's dollars per feet, the integral of a rate is going to give us an amount. We also saw that when we integrated like velocity. Velocity is a rate. So when I integrated rate, it gave us an amount. And in this case, it's like the amount of distance, the position that we have. And then this last one, F is measured in dollars per hour. DT would be measured per an hour. So what would be F prime? Dollars per hour, or dollars per hour squared, very similar to the one above it. Integrating F of t is dollars per hour. DT would just be hours. So we would again just have dollars for that fourth one. It is useful looking at units because it will kind of help you determine what you need to do in the problem. For example, say the function given to you was in dollars per hour. You knew your answer needed to be in dollars. So that would be your clue, like, hey, I need to somehow take an integral to get to the answer. So you can kind of use the units to figure out which calculus you need to do. So to kind of finish out these notes, kind of with an easy thing, just kind of 4 questions. Again, I stripped this completely of the context. There's no word problem around it. But like in that first one, say the word problem, all the functions had units of feet. You knew your answer needed to be in feet per second. In that problem, to turn feet to feet per second, would you want to take the derivative? Would you want to integrate, or would you do neither of those?
Differentiate.
Differentiate. So we have an amount going to a rate. Whatever that function is, we're going to take the derivative, which we'll start doing a little bit more next week when we have actual word problems to do. What about meters per day to meters? What math operation would turn meters per day to meters?
Integration.
Integrate. This one's a weird one to think about. What about cubic feet to square feet? And it might help if I write the units out with cubic feet and square feet.
Differentiate.
Differentiate. And then last one, I'm going to bother asking, if your function is given you to in inches and you know your answer needs to be inches, then just use the function that was given to you. So we're going to build on this idea on Tuesday again and start looking at actual kind of types of word problems that these problems can ask us. Your homework assignment, so pretty much today and literally all next week, we're just going to be working on a single homework assignment. So don't get like freaked out when you see how long it is, but it's a week's worth of work. But it's homework number 4. I have it divided into 3 parts. We have part A, we have part B, and then part C, and hopefully my surface unfreezes in a second. There it goes. So part A is what I want you to go ahead and start working on now. It's basically this rewritten version of the first FTC without the context, without the word problems, and all of that. Tuesday and Wednesday, we're going to be looking at the word problems. Probably will take us 2 days to get through them. And then after we do all the hard word problems, we're going to kind of wrap back up and do PVA, which becomes a little bit easier to do after you do the hard stuff. And we're going to be doing that on Thursday. So that's kind of how our next week is going to look. Again, I do recommend, I know it's a long weekend. I'm not asking you to spend your whole weekend doing calculus, but doing some of that part A will just make next week go a little bit better for you, where we have things like without context, and then you can kind of scroll yourself and look at part B. You can kind of see the types of word problems you're going to be expected to do. Again, this is always question number 1 or 2 on your AP exam. Like I can guarantee you, you're going to see a problem with this kind of topic. I'm going to finish grading your quizzes today during office hours. Once I get those graded, I will post the answer key in case you want to go ahead and start looking over your mistakes on the quiz. Other than that, it's 1 o'clock, so class ends in 10 minutes. But if you are good to go, then I will see you on Tuesday. If you